Hi, Year 12. So we continue with chapter 13. So we're going to look at resolving a vector f along um, or Cartesian plane, so our directed vectors I and j. So I and j, when you define it as a Cartesian plane, it will be two unit vectors that are perpendicular. From I to j will be anti-clockwise, but when we deal with inclined plane, you will see that we can rotate those ones um, to fit the slope of the plane. So here are the diagrams coming. You have a vector f is of magnitude, theta is the angle to the positive x-axis, and using our right angle triangle we can determine the magnitude of each component. So what's important here is the adjacent is f, the magnitude of f times cos of theta. Then it's a vector, so it's in the direction of I. The perpendicular vector is magnitude of f times sine of theta times j, as it is a vector. Now if we look at just the magnitude of the two sides, the difference is going to be here, it's going to be cos of theta, which is our adjacent, okay, and the opposite will be our sine of theta. Both of them times the magnitude, and that's what's really important to remember to use for this exercise. Alright, let's look at the situation when have a look at this example. Pause the video. The first thing you need to do is do a diagram, annotate everything that you know given to that in that paragraph. So what's important is going to be the direction of the vectors, their magnitude. So direction meaning the annotate the angle, but also make sure it's in the I guess the correct direction. Alright, let's come back to this. What I meant by the correct direction is as you're pulling towards the right, don't forget that the friction force has to be in the opposite direction of the movement. If you put it in the opposite direction, you're gonna it's gonna be a sort of a thrust force in the same direction, which contradict all the physics of the situation. Once you have your diagram, so we have a reaction force, we have a weight force downwards. The pull force, it's along a horizontal plane inclined at 30 degrees, so here is the angle, and then you have to annotate your unit vectors, okay, and then the biggest systematic part you will do in all situations for this exercise, you need to resolve in the I direction and resolve in the j direction. Why are we doing this? Is we want to create equations. In this situation we have from the graph there's one unknown, the reaction force from the plane onto the block, plus another one which is the acceleration of the block. So we have two unknowns, and when we do those two resolution, we're going to end up with two equations. You solve the two simultaneous equations and you get the r value as well as the acceleration. As here we only need the acceleration, you probably will substitute the r value from one equation to another. Also, when you resolve in specific direction, for example, if we resolve in the vertical direction, because the friction force is perpendicular, this element will disappear, will be equal 0. In the other direction, when we project in the I direction, because the weight force and the reaction force are perpendicular, they will their component will be 0 in the I direction. So you resolve respectively in both directions. We have an expression of R in here, which is an exact solution. We're going to substitute that in this second equation. And then we estimate the acceleration. Again, it's a positive value, meaning we moving in the I direction is to the right. Pay attention to the sign. If your A value was negative, it means you will be moving to the left, which would be a contradiction. All right, next one. So this time we're gonna look at an inclined plane. Again, the first thing you need to do is draw a diagram about and annotate the forces, the direction, make a choice for your I and j vector, and yeah, have a go at this. Pause the video. Alright, so once we come back to this, the diagram. Again, you have your particle here. Weight force is vertical. Annotate the amount. The reaction force has to be perpendicular to the inclined plane. The inclined plane has an angle of 30 degrees, and there's a pull force that is acting up the plane. So as it's acting up the plane, it's not vertical, it's really along the plane. The acceleration of the particle down the inclined plane, that the acceleration is going to be in the same direction as your the pull force, and we'll see that when we resolve along I and j. In terms of a little bit of angle properties, let's move on to solving, but I'm gonna annotate some important angles you need to remember. When we resolve, so magically they come up with this angle. What I like to do, and it's gonna be the same for all inclined plane, is I'm trying to get my pen. Okay, so whatever angle you have here, it's gonna be, if you extend the reaction, which is perpendicular to the plane, that angle is also of 30 degrees. Okay, so or I is parallel to the plane, or J is perpendicular. I know it's annotated there, but it's not really clear. I like it to be explicitly separate. Alright, so first we resolve in the I direction. So in the positive we have 15. The reaction is 0 because it's perpendicular. And here we have our 5j, which is the opposite side we need to project. So it's going to be, because it's in the opposite direction of I, it's going to be minus 5j, and it's going to be sine, because it's the opposite, sine of 30 degrees. Now, from our trigonometric properties in different quadrants, negative sine of 30 degrees is exactly the same as cos of 120 degrees. So really up to you. Now, we resolve in the I direction. What we have, all that amount that is equal to negative 19 over 2. If we apply the Newton's second law of motion, it's equal to the mass times the vector acceleration, and the acceleration as a vector is only in the right direction, so we're going to call it A. So now we get the acceleration, which is a deceleration. So basically what it means is the particle is moving downwards along the plane. Now if we resolve in the j direction, which is the parallel to the reaction force, we have a reaction we have a weight force. Again, if I use my 30-degree angle, because it's downwards, it's going to be negative 5j. From that 30 degrees, it's going to be the adjacent, so it's going to be cos of 30 degrees. So I like to use that 30 angle property because the adjacent is cos, the opposite is sine, and we don't muck around with like random angles of 120 and 150, and you don't know where it's coming from. Okay. Now once you substitute, we get that expression r minus that amount equals, again, it's the Newton's second law of motion. The right hand side is m times the acceleration in the y direction. But because the particle is moving along the plane, that vertical component is actually equals 0. Then we resolve for r. Okay. So we have the r, and then we have both elements, so we have resolved this question. Okay. All right. Last example. Pause the video. First thing you attempt, make a diagram as complete as possible, and we'll come back to this. All right. With the diagram, what's important? Again, you have the reaction, the weight force. You have your I and J tilted with that angle. Again, I have that angle here. That is the same as my theta here that we don't know yet, but there's a way to figure it out because we know the tangent. What's important? Okay, so it's moving up, so it's going to move in that direction. That is why our friction is going to be going to the left. Okay, now just be careful. In the second situation, what is the speed of the particle when it returns to its starting point? So as long as it's moving upwards, it's probably gonna have a deceleration, so it's gonna come to a full stop, and then it's gonna come back down, and then come back to the starting point. Now when it comes back down, it's a second diagram. You need to change the direction of the friction. The friction has to be on the right because this time the particle is going to slide back down. But first we need to calculate the value of v. So what happens is it's traveling, it starts from, let's say it starts from here at a velocity of v, which is going that way, and at that endpoint it has a velocity equals 0. You can also solve that using your equations of motion for constant acceleration. That will work as well. Okay, because anything linked to gravity, even with friction, it's a constant acceleration situation. Anyway, here we're just going to deal with just in a slightly different way. All right. Okay, so we need to resolve that in the two directions. So in the j direction, again, remember you have no acceleration, so it's going to be they took a little bit of shortcut here. So when they resolve it in the positive direction, we have positive r minus mg cos of theta. Okay, and again, how did they get that cos of theta? Again, a reminder, extend that line, that's theta. Okay, and to get along the j direction, we need to take the adjacent component. So again, it's a right angle triangle here. We know that's the magnitude mj, and that's the hypotenuse of a triangle. So we have, again, we need two equations. R is unknown as well as our acceleration, so we need to resolve for R and then substitute in the other equation to find the A amount. We keep J as a constant. It's just easier to manipulate than 9.81. Now, as we know, tangent of theta is 4/3. Again, that's a little bit of a trick. Is you draw your right angle triangle. That's our theta. Tangent of 4/3, because it's a ratio, it's opposite over or adjacent, so it's 4/3. Using Pythagoras, we evaluate the hypotenuse, which is a whole number. Okay, and by using our SOHCAHTOA or trigonometric ratio, cos of theta is 3/5, and if we need sine of theta, it's gonna be 4/5. Okay, so the reaction is here. All right, now we resolve in the I direction. So we have our friction force. We have minus mj sine of theta. Again, it's in the opposite direction of I. Sine of theta is because it's the opposite, equals ma, because we assume a is as a vector. We don't know its amount. We assume it's going in the I direction. Okay, because I is the positive direction. That's the convention. We substitute, we make A the subject, and then we have a acceleration. And again, notice how it is negative, which is fine. It's a deceleration because it's coming to a stop, and the acceleration has to be negative. All right, so we have a negative acceleration. We great. Let me move that for a second. So using the equations of motion for constant with constant acceleration, we use this expression. We know that the end velocity has to be 0. S has to be, the distance is 6. We have a quadratic equation. We make v the subject, and we get this amount in meters per second. Again, it's a positive, so it is in the right direction. So let me add that, so it's a positive. So if I go back to the previous diagram, our v will be in the positive direction along the inclined plane. Alright, for part B, when it returns to the starting point, we're gonna continue from where it stops moving. So it stops moving, which is basically 6 meters. Great. This is terrible. You probably gonna use the equation of motion. So that distance now is 6 meters. Our initial velocity is along the plane is 0, and v is when it comes back down to the start. That's our unknown. Okay, now notice with the diagram, we have a weight force here, mg, or reaction force. The friction force is this time in the positive direction of I. Also, because now you're moving downwards, the acceleration, hang on, it's really a matter of convention. No, we leave the acceleration as a variable going to the right, but it's going to be negative again. Okay, just stick with the convention when you don't know the value. Wait, hang on, no, the friction force, wait, the friction force is that way, so the acceleration has to go downwards. All right, and I was wrong. Okay, so it's a variable, it's unknown, just keep it going in the same direction of I. Again, make sure the friction force is going in the opposite direction of the motion. This time we resolve in the I direction. We know the R value from before, it's the same process. So we write positive mg here, sign, that's the opposite, that's negative, that's fine, equals ma, so a as a convention is going to the right. We resolve it and it resolves itself. A is actually negative, which is fine. So we assume as a variable is to the right, but when you draw it, it's going to be to the left now that we know its amount as a negative vector. We use the equations of motion. U is 0, V is what we need to solve for, and that gives us the value here in meters per second. So interestingly, G, they resolve it at the end. It's kind of a good practice to keep your constant as a don't evaluate them until you have your final expression. All right, and that's it for 13C, and I'll see you later.